Last time I went a little bit over time, and today I'm starting late, so I think I'll just sort of try and end around 5 because I don't want to keep you guys waiting too long. So last time I raised this question called the von Neumann-Day problem. And the question asks, do there exist non-amenable groups that do not contain F2? And I mentioned that this problem was solved by Olshansky in 1979, and subsequently further examples were given by Adian. These are the so-called Tarski monsters and the so-called Burnside groups. These are finitely generated but not finitely presentable infinite groups with some surprising properties. And so the problem remained open for the class of finitely presented groups until 2002, when Olshansky and Sapir found a way of building a torsion bicyclic finitely presented group that is non-amenable and doesn't contain free subgroups. But Thompson's group F was sort of a conjectured counterexample to this question, and for a long time people tried to show whether F is amenable or not, and the problem is still open. And I want to sort of tell you a story that led to a construction of mine with Justin Moore that provides an example that is very close to Thompson's group F, shares a lot of common features, is finitely presented, type F infinity, non-amenable, doesn't contain free subgroups. So in a sense, the original motivation for showing that F is non-amenable, if it is, was sort of settled by this example. So let me recall groups of piecewise projective homeomorphisms again. So remember that PSL2R, 2x2 matrices with determinant 1 acting on the real projective line as follows. So if I have a matrix G and some point X in the reals, then I define G of X as follows. So this is the fractional linear transformation AX plus B over CX plus D if defined, so if the denominator does not equal to 0, and it's infinity otherwise, and G of infinity is, the convention is that it's A over C. And so this action, so this is, I'll identify this with the circle. So this action on the circle has 3 kinds of elements. The first kind is hyperbolic. So in this case, you have exactly 2 fixed points. And this is characterized by the trace being larger than 2. Well, I'll say the absolute value of the trace. And the second type of element is parabolic, characterized by having exactly 1 fixed point. And this is the case if and only if the absolute value of the trace is equal to 2. And the third type of element is elliptic. No fixed points, and characterized by the absolute value of the trace is less than 2. Okay, so you have these 3 types of elements.
Non-identity elements.
Non-identity elements, yes. So And so a piecewise projective homeomorphism of the real line is defined as follows. So if I call the homeomorphism F, then there must exist finitely many points that split the real line into a bunch of intervals, so that the restriction of, so let me call this interval ij, the restriction of F to ij agrees with the restriction of some element of PSL2R to ij. Okay, and GJ, yes. So essentially, I'm doing what we do with piecewise linear maps. I'm just copying and pasting. So I take my pieces are now projective instead of linear, and I can build a group. So this group is called H of R. This is the group of all piecewise projective homeomorphisms of the real line. And every element has finitely many breakpoints. The group operation is just composition, right?
Is it of R or R is infinity?
Of R. Infinity is fixed. So the interval that whose infimum is minus infinity, and the interval whose supremum is plus infinity, the restrictions there will be affine maps necessarily, because those are the only maps that fix infinity. So that's a great point, yes. So given a subring, I denote by PA, subset of the real projective line, as the set of fixed points of hyperbolic elements of PSL2A. Okay. So remember, every element of PSL2R is either hyperbolic, parabolic, elliptic, or identity. And I take all the hyperbolic elements in PSL2A. Each one of them has two fixed points. And I take the union of all such fixed points over all the hyperbolic elements in PSL2A. And that set is PA. And so PA is PSL2A invariant. Right? Since if I take an element that is hyperbolic and I conjugate it by another element of PSL2A, then the conjugate is also hyperbolic because the dynamics are preserved under the conjugation. And therefore, that new element is going to have two fixed points, which are images of the original fixed points under my choice of conjugator. And so this is a nice PSL2A invariant set. So now I can define a group, HA, as the group of piecewise PSL2A projective homeomorphisms of the real line with breakpoints in the set PA. Okay? So these breakpoints are exactly the points where I'm allowed to cut and paste, right? These are the points where I glue these intervals. And so now I will state a theorem of Monod. is a subring of R such that A is not equal to Z, then HA is non-amenable. Moreover, HR does not contain non-abelian free subgroups. So does not contain F2. Okay, since HAs are all subgroups of HR, none of them contain F2. So for any subring A of R not equal to the integers, H of A is a non-amenable group that does not contain F2 subgroups. So it's a counterexample to the von Neumann-Day conjecture problem. Some people call it a conjecture, some people call it a problem. I'm not sure whether they conjectured it or. So this is very nice because it gives you some very elementary examples, right? I mean, the Tarski monsters are really hard to construct, and so are the Burnside groups. And these give you some examples that come from a very natural source, this very classical action, and you do a cut and paste construction, and you get, a counterexample to a very old question that has its roots in the Banach-Tarski paradox. And so, what I'm going to do now is I'm going to give you the proof of non-amenability. So the proof that these groups don't contain free subgroups is essentially the same as the proof I gave you in my first lecture that the group of piecewise linear orientation preserving homeomorphisms don't contain free subgroups. I actually proved that for Thompson's group F, but it's the same proof. The only difference is that here the germs at fixed points are metabelian rather than abelian. So in the piecewise linear case, for Thompson's group F, the germs were integer powers of 2, so that's an abelian group, multiplicative abelian group. In this case, the germs are going to be affine, and so they will be metabelian. And so instead of taking commutators, you'll have to take second commutators. Each time you do some calculation, you'll have to take a commutator twice to get exactly the same effect. So it's really the same proof modulo that observation. And I'll give you the proof of non-amenability. The proof of non-amenability is actually rather elementary and conceptual. So I'm going to actually use some concepts that were defined in Martin's talk from before. So we call X a topological space, Polish, if it is completely metrizable and separable. So completely metrizable means that there's some metric which gives you the same topology, which makes it a complete metric space, and separable means that there is a countable dense subset. And so a standard Borel space, you just recall from this morning, is a pair X sigma such that X admits a Polish topology whose Borel sigma algebra is sigma. Okay. And for uncountable, for the uncountable case, there's a unique standard Borel space up to isomorphism, and that's all we're going to be interested in. Given a standard Borel space, we consider group actions, just Borel group actions of countable groups, gamma. And associated to this, we have the orbit equivalence relation, which was again defined this morning. Let me just recall for you. So x comma x dot g, I'm only considering right actions in my talk, where little x is in x and little g is in gamma. If you have a countable group acting by Borel automorphisms of a standard Borel space, then you get a countable Borel equivalence relation. But in fact, if you just come across a countable Borel equivalence relation in nature, in fact, it turns out that there is some countable group that acts on the standard Borel space, giving you exactly that equivalence relation. And this is the so-called Feldman-Moore theorem. Let me state that. Let E be a countable Borel equivalence relation. Then there is some countable group, gamma, acting on X by Borel automorphisms such that E coincides with the orbit equivalence relation of this action. Okay? So this is a very nice fact, just to keep in mind that these things all come from actions of countable groups. So now I'm going to define the key concept that goes into the proof of non-amenability of the groups HR, and that concept is the notion of an amenable equivalence relation. So just a quick point, by a measure on X on my standard Borel space, we mean a sigma finite Borel measure. We only consider sigma finite. So a sigma finite Borel measure is one that is defined on the Borel sigma algebra, and for which there is a countable collection of finite measure sets whose union is all of X. So given an equivalence relation in X, we say that E is mu amenable for some measure mu on X if the following holds. if there is a sequence of Borel functions lambda n from E to the non-negative reals such that one, if I take the maps lambda and x, let me just define these in a second. These maps are going to have L1 norm 1, so they will be in lambda and x lies in L1 of the equivalence class of x, where lambda n x of y is simply lambda n x comma y. Okay? So I have a sequence of Borel functions, lambda n, from E to the non-negative reals. So they take as an input pairs that are equivalent. And so I can define these functions. So for each little x in capital X, I can define a function lambda n x evaluated at a y which lies in the same equivalence class as x as being that, right? And these functions I require are in L1, and their L1 norm is 1. And secondly, there is an E invariant A subset of x such that mu of A is 1, for which the L1 norm of lambda xn minus lambda yn tends to 0 as n goes to infinity for all x comma y in for all x comma y in E such that x and y lie in A. So what does this mean? So here's the point. So I have my equivalence relation E, right? So it's a union of equivalence classes, and I'm allowed to discard a mu measure 0 set, right? So that the complement is also a union of equivalence classes, and I can restrict everything to that, right? That co-null set. And in this co-null set, these functions are asymptotically sort of converging to the same thing, okay? And so if the amenability has like a myriad of different equivalent formulations, and if you've seen the Reiter condition for amenability, which I'll recall that in a second, this is sort of mimicking that, but for an orbit equivalence relation instead of for a group. So let me. Sorry? What?
That the measure of A should be 1.
Yes.
Not that the complement of A should have measure 0.
It's going to be the same thing, right? Because okay. I'm sorry. This should have full measure. Yeah. So I'm sorry. I'm just assuming that this is a probability measure, but you're right. I don't need to assume that. So mu of x minus A is 0. Yeah. Thank you. Yeah. I mean this you can do this with a probability measure, but it doesn't have to be. So.
The two there is.
There is an E invariant, a subset of X.
This is.
Ah, sorry, yeah, there is. Well, yeah, there is and there exists and, yeah, sorry. Maybe it's a bit late in the day. So the main point here is the following proposition. Let gamma be a countable amenable group acting in a Borel way on X. A standard Borel space, and mu any measure, any sigma finite measure on X, then the associated orbit equivalence relation is mu amenable. So let's quickly prove this. So recall the writer condition. Which is one of the many equivalent formulations of.
Measure to be invariant under gamma?
No, not at all. Not at all.
You want the action of gamma to preserve the measure class?
Yep.
Otherwise, it's just a measure.
It better preserve the measure class. Yes, that's a good point. Yes. So yeah, that should be quasi-invariant. Yes, yeah. So yeah. Thank you. Yeah. It should be yeah. Thank you. Yeah. So gamma is amenable if and only if there exists a sequence Fn of functions with each Fn being in L1 of gamma. The Fn's are non-negative, and they have L1 norm 1, such that the limit of the difference of these, so this is the action of an element on the left. So the action, the group acts on itself, and so if you have functions on the group, L1 functions, then the action of the group, the left action is simply an action by permuting the input of the function. This goes to 0 as n goes to infinity. And so define the functions that we want on the equivalence relation to be simply the sum over all little gamma in gamma, such that x dot gamma equals y fn gamma. So we simply collect all of these evaluations, and by definition, the second condition will be satisfied. Both the first and the second conditions will be satisfied. Right? It's sort of tautological by definition. And so essentially what this notion is doing is it's sort of capturing for an equivalence relation what the writer condition says for amenable groups. Right? That's why it's called. That's why the notion is called an amenable equivalence relation. Okay. So now let's give you a quick proof of non-amenability of HR. This relies on a very nice theorem of Carrier and Gies from 1985. Sorry?
The Carrier and Gies paper had an error in it.
Yes, but the error doesn't affect this proof. The error is, and yeah, so there is an error. It's not that important, the error somehow, and this proof is not affected by it. Yes. So the theorem goes as follows. Let gamma be a subgroup of PSL2R. I'm going to state it in a slightly different way than it was stated in the paper. I'm going to sort of paraphrase it, but it's really the same theorem. Be countable and dense in PSL2R. And so the associated orbit equivalence relation of the action of gamma on the projective line is non-amenable with respect to the Lebesgue measure. Okay? And so from this we can very easily extract a proof of non-amenability of HA. So the proof of non-amenability of HA when A is not equal to Z. So if A is not equal to Z, then A is dense in R, and PSL2A is going to be a dense countable subgroup of gamma. So one simply has to show that the orbit equivalence relation of the action of HA agrees with, so I'm instead of taking all of the circle, I'm going to take a conal with respect to the Lebesgue measure subset of the circle. I'm going to call it X. This agrees with the orbit equivalence relation of the action of PSL2A on X, where X subset of the real projective line is conal with respect to the Lebesgue measure. So the way you show this is actually a really fun exercise. So the idea is that you take the orbit of infinity. It's, this is a countable group. So you take the orbit of infinity. It will be some countable set, null set. Throw it out, and take any point outside that, and take your favorite element of PSL2A. Acting on that point, it goes somewhere. It doesn't go to infinity. It stays inside the real line. Then you can build by hand an element of HA where the restriction on a neighborhood of that point is exactly your original element of PSL2A. And so this is kind of a fun exercise you can do, just using the definition of HA that outside the orbit of infinity, you have exactly the same orbits. And so the equivalence relations are the same. And since this thing is non-amenable thanks to Carrier and Gies, this other equivalence relation is also non-amenable. And so this is like a very nice conceptual proof of non-amenability. It avoids having to do any crazy combinatorial calculations and the kind of things that people try to do for Thompson's group F, and gives you like a short conceptual proof. And the advantage of this is, of course, Monod provides all these examples. None of these are finitely generatable, but you can actually construct a finitely presented such group, and that's going to be the last thing in my lecture. But before I...
Yeah, I finitely generated subgroup because...
Abstractly, you have some finitely generated non-amenable subgroup, but yeah, so concretely and also finitely presented, right? So that's right. So in the last 15 minutes, that's what I'm gonna do. But
why it's important to consider hyperbolic elements?
It's not important at all. You can do many other constructions. Yeah, you can. Monod just chose hyperbolic elements, fixed points of hyperbolic elements as places to glue. But you can take any PSL to A invariant subset that is maybe countable. I don't know, some reasonable subset that is PSL to A invariant. You can take fixed points of parabolic elements. You can take the orbit of 0. All kinds of things. And actually, so Greenberg considered the orbit of 0. And he showed that for certain A, this is a C1 action. And so I think Greenberg really was kind of the first person in print to have studied groups of piecewise projective homeomorphisms. Of course, Thurston knew about them, but he never published anything. But yeah. Okay, so now I'm going to talk about a finitely presented group of piecewise projective homeomorphisms. And what I'm going to do is I'm going to go back to Thompson's group F acting on the interval, and using tree diagrams, which I had defined in my first lecture, what we can do is build an action of F on the boundary of the infinite rooted binary tree, which I will identify as 2 to the omega. So this is the Cantor set of infinite binary sequences. So 2 stands for 0, 1, and omega just stands for n countable set. So this is just topologized with the product topology. It's Cantor space, and F acts on this using the tree diagram mechanism that I had defined. And so what I'm going to do now is I'm going to define a map from this Cantor space to the non-negative reals as follows. So I'm going to include the point at infinity. So it's going to be recursively defined. So phi of 0 sigma equals 1 over 1 plus 1 over phi sigma. Okay. This is a continued fraction, and phi of 1 sigma is simply 1 plus phi sigma. Okay, so if you give me an infinite binary sequence, I can apply this map sort of 1 by 1. And so I look at the first digit. If it's 0, then I get this. And then I continue applying the map on the suffix. And I keep going, right? This is the recipe to sort of keep going. And in the end, I produce a continued fraction expansion of some non-negative real, right? And so now I can sort of extend this map to all of the reals. So define this new map from infinite binary sequences to all of the reals as follows. So this guy is minus the original map applied to sigma, and this one is simply the map applied to sigma. So I'm sort of just looking at the first digit, and based on that I decide to apply minus phi or phi. Okay. So this provides a map from the Cantor space to the reals. It's 2 to 1 on the rationals and 1 to 1 everywhere else. It's a nice continuous surjective map, and so there's some miracle that happens at this point. Okay, so what's the miracle? This was observed by Thurston. This conjugates the PL action of F to the piecewise projective action to the piecewise projective action. Okay, so what is the piecewise projective action of F? I had defined it in my very first lecture. Let me recall it. By the way, this was never written down in print anywhere, and there were sort of informal sort of understanding of it floating around, but Justin Moore and I wrote it down in our paper. So again, this is sort of a definition theorem in the sense that it's an equivalent definition of Thompson's group F. F is the group of piecewise PSL2Z projective homeomorphisms of R with breakpoints in the rationals. Okay. So as you pointed out, you don't have to use fixed points of hyperbolic elements. You can, so this is a kind of a manifestation of Thompson's group in the piecewise projective setting. And yes?
In my memory,
yes.
In the definition of chapter 5,
yes.
From the beginning of 0, we should reverse all these.
Sorry. In this definition?
Yes.
Yeah. We should switch the zeros and ones. Yeah. You're right. You're absolutely right. So yeah, thank you. Sorry about that. This is absolutely right. So what we do here is we take sigma, but we switch the zeros and ones. Yeah. Sorry. Yeah. Exactly. Yes. Exactly. Yeah. Thank you. That's. And so now I'm going to do the following. So I'm going to introduce a new element. So this is due to me and Justin Moore from 2014. So I'm going to define a piecewise projective homeomorphism, which I'll call C of t. So C of t is the identity outside the unit interval, and inside the unit interval it is the map 2t divided by 1 plus t. Okay? And I'm going to generate a group called G0, which will be generated by the piecewise projective copy of F together with this element C. Okay? And the theorem that we proved says that 1, G0 is finitely presented. 2, it is non-amenable. And 3, it has no F2 subgroups. And then later, subsequently, I showed that this group is also type F infinity. So this gives you an example that is exactly the kind of example that people were looking for in the 70s with Thomson's group F. It gives you a very nice finitely presented counterexample to the von Neumann-Day problem with 3 generators and 9 relations. And so in the last few minutes, let me give you like a little flavor of how we work with this example and how we prove this kind of a theorem, that it's finitely presented. So maybe I'll just quickly change the... So I'm going to define 2 primitive functions from the Cantor set to itself. And using that, I will build a whole family of homeomorphisms of the Cantor space and connect those homeomorphisms with this group. So let sigma be in the Cantor space. I define a map X as follows. So this is 0 tau if sigma equals 0, 0 followed by some infinite binary sequence tau. It is 1, 0 tau if sigma equals 0, 1 tau. And it is 1, 1 tau if sigma equals 1 tau. And now I'm going to define another function called y, which is going to be this function, you simply read a prefix and you know what your output is. For this function, you have to sort of iteratively apply this definition. So the definition goes as follows. So this is 0 followed by y applied to tau if sigma equals 0, 0 tau. It's 0, 1 followed by y applied to tau if sigma equals 0, 1 tau. Sorry, this is 1, 0. Oh no, I'm sorry. This should be 1, 0 and this should be 0, 1. Yes. Y inverse, yes. And 1, 1 y tau if sigma equals 1 tau. Right, so the point is that you have your infinite binary sequence and you look at the prefixes of this form. So if it begins with 0, 0, then you replace this 0, 0 with a 0 and you apply y to the suffix, and you keep going, right? If it begins with a 0, 1 followed by this suffix, then you apply, then you replace the 0, 1 with 1, 0, and you apply y inverse to the suffix, and similarly here, right? So any infinite binary sequence must begin with one of these 3 prefixes, and these are mutually exclusive possibilities. So this defines a homeomorphism of the Cantor space. And now what about y inverse? So the definition of y inverse is sort of implicit in this definition. I can write it down. It's right, so these are the primitive functions that are the building blocks of this group. And now you can localize these functions to your favorite finite binary sequence, essentially just applying it to the subtree rooted at that finite binary sequence. So for S, a finite binary sequence, this is my notation for finite binary sequences, I can define XS applied to sigma as the map S followed by tau, sigma applied to tau if sigma equals S tau and S otherwise. And similarly define y of S. So similarly define ys. Sorry? Sorry. This is so this is no. So this is x yeah x yes.
And the second line should be sigma.
Right yeah sorry sigma. Right, so the point is that I have my address sigma, and I have a subtree that's rooted at sigma, and so I'm applying y. So I sort of delete that off of the big tree, and I apply x, and I glue it back. Right, this is xs, and similarly ys. I take the address. Well, in this case, this address. Sorry, this is s. Not sigma is the infinite sequence. I take the infinite tree rooted at S, I remove it, I apply Y, and then I glue it back, right? These are XS and YS. And so really the key combinatorial idea here is to sort of demonstrate that, in fact, the group G0 is generated by these elements XS, YT, where S and T are finite binary sequences, so that T is non-constant. And then once we establish this, we can start doing a combinatorial analysis of actions of these elements. And we write down words in these in this generating set, observe relations, and demonstrate that in fact there is a certain natural family of relations which in fact presents the group, and those relations can be sort of conjugated up in the tree to a small set of relations that suffice to actually present all of these relations, and so that's sort of how this group is built. So I think that I'm out of time, so I'm happy to tell you the details in person if you're interested. Yeah, so stop here. Oh, and one thing I will mention is that last time I talked about Tarski numbers and paradoxical decompositions. I showed that Monod's groups and this group all admit a paradoxical decomposition with 25 pieces. So that sort of was interesting. I mean, I was trying to show that maybe it can be done with 6 pieces, which was the smallest number you need for such a. But I wasn't able to show that. So 25 pieces is so the bounds for the Tarski number for these groups are between 6 and 25. But we don't know exactly what that number is. Okay. Yes.
Amenability of H of Z equivalence to amenability of F, or without the denseness, can you not even connect those two groups?
So H of Z contains F as a subgroup. So if H of Z is amenable, then F is amenable. But if H of Z is non-amenable, then I don't know how to show F is non-amenable. Yeah. Yes. And in fact, I showed that like for every sort of action of F or one of its subgroups on the line that is semi-conjugate to the standard action, the orbital equivalence relation will be amenable. So you're not gonna, yeah, you're not gonna get, this kind of method will not work to show that F is non-amenable.
That makes sense.
Yeah.
Could you repeat what you just said? Like,
Right, so I sort of defined this notion of coherent actions. I mean, I'm happy to tell you that later. And I showed that if you take subgroups, so one strategy for showing that F is non-amenable from this could be that, okay, I take a subgroup of F, I find a crazy action of that on the circle that produces a non-amenable equivalence relation, and that gives me the certificate that F is non-amenable. But I showed that that action has to be very, very strange. And you know, the kind of actions that we like to study will not work. And I call those coherent actions, but you know, I don't want to define that, but I can tell you later if you like. Yeah. I mean, in some sense, the difficulty with F and its subgroups is that you don't have non-standard actions. You know, you can build actions using dynamical realizations of certain left orders and so on, but you know, you don't really have actions that sort of occur in nature that are producing a complicated equivalence relation or something like that. So yeah, that's the issue. Yes.
Can you talk a little bit about the 9 relations and how do you prove that it doesn't contain F2?
So the proof that this doesn't contain F2 is the same as the proof that Thompson's group F doesn't contain F2. You know, this is a group of piecewise projective homeomorphisms where the groups of germs at fixed points of elements are metabelian. In the case of F, it was abelian. And so if you take 2 elements that you think maybe generate a free group, then you do exactly the same trick that you do with F to get a copy of Z square, or showing that that group is actually solvable. But instead of taking commutators, you take iterated commutators. So you take double commutators. So that, you know, if you have 2 elements and they have a common fixed point, then the group of germs at that fixed point generated by these 2 elements will be metabelian. It could actually be abelian, but certainly it will be metabelian. And so you do a double commutator and you get an element where that germ vanishes, but the original element that you start with has that germ, and so you sort of push the support away and you know, and you keep doing this until you get elements with disjoint support, or the group itself is solvable, right? So this is the proof that I sort of outlined this proof in my first lecture for F. It's really the same idea for these groups. For the relations, I mean, I'm happy to write them down. It will take me like 5 minutes to write. Do you want me to write them down? Essentially, there's sort of 3 kinds of relations. There's okay, maybe I'll quickly write them down. It's not. Essentially, you have this one. Okay, let me give you a couple of families in the interest of time. So one family which sort of captures the recursive nature of ys is the following. So ys equals xs, ys0, ys10 inverse, ys11. Okay, so these are the relations that capture the recursive nature of this. And then you have sort of all kinds of commuting relations. For instance, you have like yt equals yt ys, when s is not an initial segment of t, and t is not an initial segment of s. So you have relations like that. So you have relations that capture when things commute, when they have disjoint support, and then you have this recursive one, and then you have the relations where if you have some behavior occurring at a subtree and you conjugate that off of to some other subtree using an element in the group, then capturing that dynamical transfer is another kind of a relation. So you have and then you have the relations in F, right, coming from the x's. So you have these 3 types of relations. And you can show that once you write down all these relations, they're sufficient. So that's the hard part, is to show that these relations suffice to present the group. And once you show that, then it's very easy to show that. In fact, only 9 of them are needed. Yeah. Yeah.
Is
Yes.
element C?
Yes.
Does it have to be the specific C for everything?
You can choose other elements and get finitely generated non-amenable groups, but I have no idea if they're finitely presented. Actually, you can do something fun, okay? So take the element D, dt equals t plus half, just very simple element, and take the group generated by F and D. It's non-amenable and no free subgroups. But I have no idea if this is finitely presented. And actually, I think that this was the first example that we came up with, that we tried to show is finitely presented, and we could not. And the 2t over 1 plus t element worked really well with the combinatorics, with the continued fractions and so on. And this guy, till date, I don't know if it's finitely presented. And this is kind of crazy because d square lies in F. So d square is translation by 1, and that lies in this copy of F. So you take F, you take a square root of an element, and you just generate a group, and that group is non-amenable. So it's kind of tantalizing. Yeah. I mean, I also tried really hard to show that the amenability of F is equivalent to the amenability of this, but I couldn't. So I don't know. There's something very strange going on. So yeah. Yeah, so this group and H of Z, I think people should study this. Like, if you guys are interested in these groups, I think these are really fantastic. Yes?
In the theme of the conference, have you asked AI whether you can get fewer relations?
No, I haven't asked AI. Actually, maybe I should, yeah.
I mean, is that something that it could actually calculate?
I somehow have a feeling that you can't do better than 9 relations. I don't have a proof of that, but there is some sort of heuristic that you shouldn't be able to reduce the number from 9, but I'll ask AI, why not? Yeah. I have asked AI if F is amenable many times. Yeah. But, yeah. AI is not good enough. It tries to do certain things, and it tries to do some computations, then it gets stuck and it apologizes. And it says that, this is really the right approach, and then it works. Oh, actually, it's not quite right. There's a counterexample. I'm sorry. So it's it's kind of a crazy experience.
It tries to make you feel good too. I think you're on the right path.
Exactly. Yeah.
So does it say this
Yeah.
is the right approach sometimes towards amenability and sometimes towards non-amenability, depending on when you ask it?
That's a good. I only tried to ask whether I only tried to nudge it to show that it's non-amenable.
Like if you asked it to show that it was amenable, I bet it would try something.
Yeah. So I should do that. I should try. I don't know why I'm pushing it towards non-amenability, but yeah.
Have some faith.
Right. So yeah. I mean, I don't know. I hope that this problem gets solved in my lifetime. Like if AI can solve it, then that would be very interesting. Yeah. Great. Right.